This is the first event of what's going to be a sequence of, we hope, interesting events for people around semiconductor design, system on chip design, embedded system design, as part of the newly relaunched network called DESN or Design. So actually, if I go back about 7 or 8 years, TechWorks, formerly known as NMI, over the last 20, 30 years, we had a network called NMI Design that was really quite vibrant with something like 110 members. And we're on a mission to rebuild that back up, especially given that semiconductor systems design is something that the UK actually has a really significant global strength in. So, next slide. I think this clicker's working. There we go. I'll do it manually. Okay, so I'm doing the welcome and introduction. Oh, it is working now. Yes. Thank you. So I'm going to say a few words about TechWorks. So I'm Charles Sturman. I'm the Chief Executive of TechWorks. For those that don't know, TechWorks is the UK trade association for deep tech and or semiconductor companies. So across our community of 300 member companies, we operate 4 networks or 4 distinct communities. Each one has a network director that leads that, a full-time member of our staff. Gillian Hughes here is the leader for the design network that we're here to experience today. Those networks are Semiconductor Manufacturing and Equipment Supply Chain, NMI, Design, Semiconductor System Design, ASIN, AESIN, which is Automotive Electronic Systems, and IoTSF, IoT Security Foundation, which is about cybersecurity and connected devices. So what we do is bring industry together at the engineering and the business level to collaborate, to help each other to grow our activities and our ecosystem in the UK, and also to develop and innovate new solutions and business globally in the global electronics industry. The wrong way. Try down. There we are. This slide just gives you a kind of a snapshot of both the networks we operate, but also the wider ecosystem of industry bodies and players that we interface with on a kind of a day-to-day, weekly basis. And you'll see some names there like SEMI, which is the Global Semiconductor Industry Alliance, Silicon Catalyst, which is US and UK, and also now Europe, and I think India, chip startup incubator ecosystem that we collaborate with as well, and various other bodies, including several government agencies, especially the Department for Science, Innovation and Technology. And sorry, Callum, I'm going to pull Callum out, who's from DSIT.
My name is not Callum.
Sorry, Hamish. So yeah, and actually the reason I did that, Hamish, because I'm so pleased that you've come today. I know you're all very busy in the department, but you know, we have some good interaction and discussion with DSIT, and they're very supportive of what we're trying to do in terms of bringing the industry together and grow what is a successful industry in the UK. Okay, so that's enough from me. I'm going to hand over now to Gillian, who's going to introduce you to the design network.
Thanks, Charles. I don't know if any of you know me, some of you do. I was formerly the network director at TechWorks, but in the manufacturing sector. I briefly left, I came back as head of semiconductors, but my day-to-day job is for the design community and building that up. I've been in industry for over 25 years, predominantly in the manufacturing sector and working with equipment refurbishers and small OEMs in deposition technology. So the design network, I'm really excited about this. It's going to be focused on supporting the UK system and chip design. So we've got big ambitions for it. As Charles said, it used to be a thriving network within TechWorks. And what I'm here to do is to grow the network with new members, have some special interest groups. I'm not going to go through them all, but these are interest groups that, after speaking with industry and with some of our members, these are groups that are of interest to them. But more importantly, work together as an elite network of professionals, individuals, companies, researchers and academics. We're We're also partnering with Silicon Catalyst. Sean is supposed to be here today. I think he's running late. Sean's a true inspiration of many of you know, and he did pick up the TechWorks Contribution to Industry Award a few years ago, a total credit to our industry. In addition to that, we're also partnering with Semi Europe, basically to expand our network out with the UK and look at opportunities for collaboration. And we're also working with similar trade associations globally to look at opportunities there as well. It's an exciting time for semiconductor design, a UK strength, as we all know, and we're working together. Hopefully we can tackle challenges and seize many new opportunities. We have got a few more events coming up. We've got the FPGA Frontrunners Group, and we're also working with IMEC. I think Bruno is here today, and we're going to be doing a breakthrough technologies. I'm going to say show. We're going to be going around the UK, different areas, different technologies. If it's something that you're interested in, then please let me know. So basically, I'm here to grow the network. If you're interested in joining more events like this or one of the special interest groups, networking with your peers, or basically just coming along, feel free to speak to me or one of my colleagues here today. I won't go on too long. Apologies, my notes. I would like to thank obviously Cadence and Synopsys today for their sponsor, the attendees, and obviously the speakers who make these events possible. Obviously, a special thanks to Mike Bartley, who's been supporting me as I transition into this new role. He's been a great help to me. So, as you know.
So, first of all, thanks very much for letting me speak today. I'll share at the start. I'm here on with the permission of Accelerate AI, but I'm not actually speaking on behalf of Accelerate AI. So, if you were hoping to hear about edge-based inference, vision processing at surprisingly affordable prices, you can talk to me afterwards, but that's not the purpose of this today. So just go back and it's all up, you can see it. So I've been doing this for 25 years, bunch of companies, mostly working on processors and SoCs. To caveat some of the stuff later in the presentation, I've never really worked on safety critical logic, which does take a little bit of a different turn, but have done a variety of tape-outs, 17 tape-outs from the good old days down to 6 nanometer and below these days. And one of those companies is still in the UK. So, so first of all, this is my general thoughts about AI. It's not a super technical presentation, but first thing I did was I asked the media, what does AI mean for us? And these are actual quotes. I got them from proper sources. They're only slightly out of context. So initial things, 40%, 60%, 50% of people's jobs are going. Everyone's going to get employed, which is probably why Elon's looking to get a nice government pension at the moment. But yeah, it's pretty doom and gloom if you ask the media as to where our jobs are going to be going. So I went to the next one and I asked what history tells us. So you can look at a few examples from history. I chose the classic one of the loom, where people were terrified in the early 1800s that the mechanical loom was going to make every person unemployed in the country. But that actually didn't happen. How loom came out, people started making more woolen products, actually increased the amount of people working in the textile industry, and it created an entire new industry in the loom making industry. So that actually made a big difference to employment in the UK and across Europe. Second one, much more recent, 1970s, 1980s, ATMs got introduced in the US. Everyone thought that every bank teller in America was going to be made unemployed because we'd all be doing it through machines. Again, didn't happen. ATMs actually meant that more people put money in banks because they could get their money out of the banks. And it also meant that people in banks spent more time doing what banks want them to do, which is selling high interest accounts to people so they could make more money. It actually meant to more bank tellers because they didn't do all their time wasting counting out cents and dollar bills to their customers. They sold them products instead. So I went to the next example of what does AI tell us about what AI is going to do to the industry. And the first thing I thought, I'll go for a fun image, generate a cartoon image of a turkey voting for Christmas, because that's the title of the presentation. And what did I get? I got a warning saying turkeys voting for Christmas is a dangerous phrase and that it won't generate me an image. So that made me quite worried that this presentation I chose the title for 6 months ago, maybe more controversial than I was hoping for. So I asked it a bit more. Image of a turkey, the animals, you don't get anything too worried. In a paper hat, make background, winter snow suit, next. And that way, AI does actually give you a picture of a turkey, voting-ish for Christmas. Incidentally, if you ever want to do this, Macs have just released their image playground. You can type turkey into the image playground, it will never give you an image. You can type Thanksgiving bird and you'll get a picture of a turkey, but you can't type turkey into a Mac. So a bit more, what does AI generally know about verification? Big question. Generate a word cloud on subject to silicon verification. And all these words are pretty much right. These are the standard bits and pieces you'll get for any interview you interview for a verification role. Almost all of these words will definitely come up. Slightly dumb that the word verification is the biggest word when you ask about functional verification, but it shows that AI does actually know roughly what it's talking about. It's not, it doesn't think we're talking about carpet fitting or anything else. So I asked it, how will AI affect the silicon design verification industry? And these are the six points we'll go through. So this is basically the presentation. I'm going to go through these points and see if it makes sense. So the first one, automation of verification processes. AI enables the generation of automatic test bench, coverage gap identification, efficient regression, all the good things that you expect it to give you. Now, I have some thoughts about this. Holy Grail, poison chalice. So we've seen this before, functional coverage versus code coverage. We know this is a standard interview question. Relying on the design to be the source of truth is flawed. That's code coverage. We know that it has massive problems, that it will only tell you about things you've actually written, not things you intended to write. Relying on verification to be the source is also flawed. Functional coverage, it all depends about how much functional coverage you write and how good it is. The big problem with functional coverage is the human squishy bit between the computer and the keyboard, where we either don't specify the correct functional coverage, or we don't code it correctly, or we just make bugs. Direct testing versus constrained random. This is a big thing I was going about. I was around in the late 90s, early 2000s when constrained random came out. Versity, big thumbs up to Versity, great company. Bugs aren't always where they are, you say you are. So directed testing, yes, it will get you to your coverage points quicker, it will get you to your code coverage quicker. But the whole point of constrained random is that people are flawed and they make mistakes. And that debug process is actually the big thing about the quality of the verification code you're doing, not the coverage closure itself. And full formal proof, this is a much more recent one. Formal proof is great. Formal proof does work really well. It can be very effective on certain designs, but it is very hard to predict. Anyone that's a verification manager will know that the standard S-curve we expect through simulation is brilliant. It tells us where we are through the project. We've had it for decades. We can pretty much predict when we're going to get to the end of a project reliably. Formal is nothing, hopefully perfect. Now, I know that EDA companies have sold certain things to do this, but I've still not seen a particularly great solution for this. And the human error is the biggest flaw. If you think that constrained or directed testing or writing coverage points is where the human error comes in, properties are massive. If you write the property badly, it will be proved and it will tell you that everything's fine and it does absolutely nothing. So you can't actually see this. This is a picture from Back to the Future. Haven't we seen all these things before? People have tried to sell us automatic test benches and automatic coverage closure many times before, and I'm old and cynical. Independence is really the key to verification. It's not only understanding the specification, you have to understand and challenge the specification. The easiest way to actually not have a verification bug is to get the spec right in the first place and make it easy to verify. You also have to understand the context, particularly as designs are getting bigger, and we'll talk about this a bit in the future, the context of when something is relevant. The hardware is almost infinitely more capable than the use cases that it actually needs to support these days. If you attempt to cover everything you possibly could, you'll probably never tape out and you'll probably miss something very important that is actually critical to your project. And that's where understanding the consequences comes in. You have to understand how important bugs are. I always said that I've never taped out a chip without bugs. I intend to never tape out a chip without bugs. It's not about not having bugs, it's about not having bugs that matter. If you don't have any bugs, you spent way too long verifying the thing in the first place and you probably missed your market and someone else is beating you to it. And this seems obvious, but verification designers tend to make different mistakes to design engineers. That's actually really important, having a different skill set, a more software-based and more user-focused view on what the design should do is actually very key to doing something stupid that's different in a different way to the designer. And accountability is essential for verification. It's not what you guys like. So every time I tape out a chip, Everyone has to sit around the table and say they don't know any reason we shouldn't be taking out the chip. I have to look them in the eye and I have to get their approval that they are happy to take out the chip. And I don't know or is not an answer in that question. You have to be confident there is nothing you know is wrong when you take that chip. No one's ever finished. There's always risk, but people are paid to make rational decisions about what that risk profile looks like. You can't fire a chatbot. Huge opportunities to improve this process. And this is the positive side of it. And it really comes down to this Mark Twain quote here again. It says Mark Twain, you can't see it. Success is a journey. Many, in personal opinion here, many verification improvements, and there have been a lot, UVM and everything else, been many improvements over the last 20 years. Most of them being focused on methodology and not usability. As chips are getting bigger, more complicated and more programmable, actually the usability is becoming a bit of a problem. And we'll go to that more. Metric-driven verification is focused on the data and not the insights. I think there's been a couple of good presentations about this in the last couple of years. We can produce way too much data now. It's very hard to actually analyze it and see if it makes any sense. This is something where AI could be a big hope. AI is very good at processing data and summarizing it in a very concise way. And reduced hardware costs, so we can now buy very good processors, very good boxes, and there's very good EDA licenses and tools that are actually quite affordable, and you can get a lot of compute for not a huge investment in a general company context. Engineers' time is actually more valuable now to the company than the CPUs or licenses in general. And that's where people spend most of the money. Second one, faster debug and simulation optimization. I'll let you read that, but we'll move on. So this is where I think there's actually divergence in the design world. There's two very different tracks that companies are going down. There's the IP and custom design solutions. And this is where actually there's probably a bit more in the UK than in other parts of the world. Novel new designs, new interfaces, things like Rob just talked about the interfaces between chiplets. There's always evolving standards, and these are generally very focused on a specific thing, either performance, power, or cost. This is where startups and young stage companies really differentiate against the big boys. They can do something novel, innovative, fairly self-contained because they're limited in either scale or programmability. And then you've got a large integration, which again is pretty much what Rob was just talking about. This goes all the way through from SoC design through to chiplets, where you're putting very highly configurable and massively programmable designs in places, often multiple ISP suppliers. In the case of chiplets, possibly even different processor nodes and completely different technologies. And they're hugely complicated interactions and a massive design space. And this is where I think there's a few different things going down. So again, AI generated image of what traditional HDL verification looks like, sitting in front of a massive blackboard, not looking at your screen. So traditional problem for EDA, and this is pretty sensible. It's a closed system. You've got much more. You've generally got shorter runtimes, and by shorter runtimes I mean in the minutes to hours as opposed to the days or months. And they've got traditional ways of doing failures. So we've got assertions, we've got data checks, storeboards, XPOPs, formal events, standard stuff we've all been using for a number of years now. And you've got traditional methods to identify how the stimulus relates to the failure. So you've got code coverage, functional coverage, parameters, test definition. And the EDA companies particularly have a large internal pool of data to go from. So these EDA companies don't just sell EDA tools, they sell IP, they license PHYs, controllers, Macs, standard logic. They have a colossal pool of pre-verified technology where they can train their AI on. And they have traditional test benches where they can get the best information. And also, more importantly, possibly to them, is there's conventional ways to monetize this product, which is very important to companies that want to make money. So there's small demos that are easy to construct. Anyone that's dealt with EDA knows full well that they produce things that make their tools look good, understandable, and they're generally small and easy to understand. They're also, these kind of things can be sellable to multiple companies because most people want this kind of thing. And it's a familiar IP and licensing flow. They can sell licenses, it's got runtime, you use it, you pay for it. And this is where systems, I'm sure there's a few people presenting later this afternoon, the kind of tools you'll see this afternoon probably fit into this category quite nicely. And they will be useful. I'm not knocking this as not a criticism, these will be useful tools. But then you've got The larger integration problems. And yeah, this is exactly what our office and Accelera looks like. Multiple things, large holodeck, where we slowly build the chip up in virtual reality. But it's a real tough challenge for EDA companies. So it's an unbound system. And what I mean by this is you've probably got multiple processors, each running a different compiled piece of software. You've got potentially encrypted or compiled code for at least one or maybe multiple pieces of IP, or even the software. And the piece of software could even be something as complicated as Linux or Windows or an inference engine, right? And you've got very long runtimes. These could be days, weeks, months of runtime, even on the emulator, to hit the actual use case. And it's very hard to identify why the test has failed, because sometimes the test may or may not fail. It might be a soft, fuzzy logic subtype. You've got hardware failures, you've got software failures, you've got interactions between hardware, you've got performance and functional bugs. Particularly in AI space, the performance is actually just as often critical as to why something has failed as to just getting the answer wrong. And then you've got accuracy and post-run analysis. So something AI do, we run a test. Does this video contain a picture of a yellow car? Somebody's got to look at that video and say, is there a yellow car in it? How do you know if the software, the hardware, and the actual grading of the system is correct to do that? And then you've got multiple sources to identify the use case. You've got the data set that you were running on, which could be huge. You've got temporal variation. So you might have frame rate in a visual process. You may have randomization within fuzzy logic. A lot of AI stuff now uses true random numbers in order to optimize the results they're getting. So it's not a simple one-to-one mapping between this is my test, this is the failure. And there's a really small pool of internal data to train from. So most of this stuff is proprietary to companies, and these kind of large designs are not available on the internet. You can't find them. People are monetizing, which makes it hard to monetize. So this is very complicated and very domain specific. You'll have very different solutions for AI chips versus visual processing chips versus graphics cards versus anything else. So it's a hard one for the EDA companies to sell you an all-in-one bundle. But you can still benefit from using AI initiatives. So obviously I did this a few months ago. I would have put a DeepSeek logo on. I'm not being racist on that one. But yeah, all these things continue. VS Code, NeoVim, all the various co-pilots are all available. And if you're not using a co-pilot to edit your code, you really should be. They've changed massively. If you haven't done it for a couple of years, the quality of the code that code processors are producing is way, way better than it was 6 months ago, let alone a year ago. You have to help yourself. Accelerate the simple stuff. So this is by the way, I've not anything you see with box I've cut and paste. This has not been edited. This is straight into a large language model of your choice. Even where I spelt or got the grammar wrong, generate an assertion for an NXI interface. It can produce you pretty good assertions. They're visual. They're actually pretty correct. You can generate much more complicated ones than that. That takes a second to generate. And you can use other things. Log-based debug. This is something I've been talking about to people for a long time. The bigger the design, I can't remember the last time I looked at a waveform to debug something as my first point of call. It really is the last resort to look at a waveform these days. Log-based debug is the way you have to go. Anything that runs for a long time, has complicated interactions, produce good logs, associated data. We used to debug it with grep. You don't need that. LLMs are really good at consuming vast amounts of log files and summarizing it for you. You can do that. In-context error analysis. If you ever type an error message from Questa, Excellium, Calibre, you'll be surprised what the errors, the information you get out. ChatGPT understands the error messages from those tools. It can tell you how to fix your problem. Data sheet parsing. Everyone knows data sheets you buy. If anyone's bought a off-the-shelf DDR or PCIe controller, the data sheets are massive. They're quite hard to read. They're sometimes quite badly written. But again, Microsoft Copilot is really good at parsing PDF files. You can ask it questions. You don't have to search. You don't have to know the word you're searching for in order to get the answer. It can massively accelerate what you're doing. And use more prevalent languages. And this is a big one. The internet is full of C code. It's full of Python. It's full of HTML. It is not full of System Verilog. It's not full of PSL. If you can switch to languages that the internet understands, you'll get much better answers from using a large language model. Let AI help with communication. Engineers, verification engineers in particular, are terrible at communicating. It's not easy, but all engineers, anyone who's worked for a startup knows, documentation gets done when everything else has happened and you eventually force someone to write some documentation. So AI generated round robin arbiter entitled add comments to Sphinx documentation. I've got Sphinx documentation. It's mostly right. But either way, that took 1 second to generate. I can read it and I can fix it in 3 seconds. And there is no excuse for anyone to have not documented their code anymore. There is no excuse for not being able to produce a report that managers can read because you can just get it to output it. And yes, it will have bugs in it, but it takes less time to fix the bugs than it takes to write it from scratch. How will the last one, proactive prediction and continuous learning? I don't think this is very likely. There's a few reasons I think proactive prediction seems unlikely. It's because we've never done it before. We have loads of program managers, we have project managers on every project we worked with. We are still terrible at predicting how a project will go in general. Big companies are better. Why are big companies better? Because they set themselves very long targets and they expect to hit them. If you're trying to be super aggressive and be very quick in what you deliver, you will always slightly underachieve what you want to do. That's, again, not criticism. It's how you work. When I was at NVIDIA, we always hit our deadlines, but that's because our deadlines were set because we had 1,000 software engineers waiting for that hardware. So you move the timescale to make sure you hit that target. But it's not easy for a number of reasons. It's heavily reactive. So one of the biggest things that affects how long your project takes is the quality of the design. And that quality of design comes down to clarity of vision on what the product's meant to achieve. It comes down to the availability and the quality of the designers and the verification engineers you've got to. And you can't have a team of all rockstar designers or all rockstar verification engineers. People will have a range of abilities from graduate through to principal through to fellow. And these products change requirements all the way through. You don't know if the product it takes 18 months to 2 years to make a chip and get it out to market. The industry changes during that time. Features will change. IPs will become available. Competitors will move ahead of you. You will have to change specs. You'll have to run with it. And that does break your prediction scheme. So you can use these tools to help improve the process, but I don't think you'll be able to put in a complicated project into a chatbot or anything and expect to get a good result without human interaction as we do at the moment. And then the last one of this, I put down the Moneyball challenge. I've mentioned this a few times. The trouble is, if you let large language models look at your Git repository, you let large language models look at your code repository, and you track bugs and you track things, the person who's going to tell you is who your worst designer is. And no one wants their name at the top of a list where AI has told them that Bob is the guy that introduces the most bugs in your design. Now, that's a management problem. How are you going to do that? You have to handle training and ranking people. We all do it. We know that teams have hierarchies in terms of ability. Putting it on a presentation and letting AI show it to everyone is not a good option. And continuous learning also has challenges, and this is our own fault. It's a highly proprietary industry. We're all doing this to make money in general, and for that reason, we're very secretive about what we're doing. We don't all open source stuff. Obviously, we just saw the presentation about ARM open sourcing their standards. We know there are multiple reasons why they are open sourcing their standards. Some of it is generous, and some of it is for other reasons. Not saying it's a bad thing at all. But we also have a hugely profitable legal industry in IP protection. All our companies have massive legal teams. We protect our IP for very, very good reasons, and that's why it's not on the internet. And possibly the most important is that we are generally one of the industries that has really innovated over the last 50 years. The quality and the size and complexity of things compared to just 10 years ago is massive. A chair is still a chair. Sofas are basically made in the same way they were 50 years ago. My phone is very different to the one I bought 20 years ago. And the pace that people are developing at is a great thing. It's going to make it very hard, even with the amount of intellect that's going into it, to keep up. And the final one, challenges and opportunities. This is all that actually matters. This is basically what this presentation is about. It's the last slide. And so this is my challenges to EDA guys. So I know they've got can't. AI is a long game. If you look at what solution companies, OpenAI, Microsoft, Google, Meta, all these companies are doing at the moment, they are giving away their AI technology in general because they're all lovely guys that want to give away their technology. But they're focusing on adoption, and we need to do the same thing. We're going to have to focus on people adopting this. I see it that my generation, or most people's generation here, we got used to using search engines, which our parents' generation didn't have. We knew how to Google something, they did not. There is a slightly different way you have to use LLMs and visual processors and things like that. If we don't adopt the way that it works for this industry, we'll fall behind. And the best practices take time to evolve, and we need to avoid the mistakes of UVM, system verilog coverage, open coverage. So UVM, I know I knock it every time I speak. It's good. It created an industry. It meant we could hire people. It set a methodology. Again, diversity, great setup. The problem is it hasn't changed in 12 years. And it didn't change because it got adopted very quickly, and it got locked down because all of us had loads of test benches and loads of IP invested into it. And we never fixed the bugs in it that we should have fixed a long time ago. And it's now staying. System verilog coverage, exactly the same. System verilog introduced functional coverage. There are many flaws in functional coverage in system verilog, and we haven't fixed them because everyone's using the old stuff, and no one wants to address the fact that you can't write most of the coverage you want to write in system verilog because it doesn't support it. So we need to focus on what AI strengths are and what the engineer's weaknesses are. User experience and personalization. This is, for me, quite a big one. I've given up attempting to convince people that I work with or work for me to use Nedit or Vim or 4 spaces instead of 2 spaces. But what AI can do is it can improve the quality of people's codes in a way that is suitable, in a way that matches their natural coding style anyway. So you get the general improvements, you get the quality improvements, but you don't have to force everyone into the same bucket. And that leads to the second point, which is avoiding debug as much as improvement. So if you haven't used a Copilot and started typing a state machine in system verilog, you create your state variables, you type paste, and then it goes, would you like, you appear to be writing an FSM. Would you like me to fill it out for you? Yes, I would, thank you very much. And then you don't get the basic errors that you get from type, cut and paste. It can do a much better job than basic cut and pasting. And then going back to the reporting, you can explain complicated data into multiple contexts without having to analyze that data yourself. You can summarize it for a manager, you can summarize it for a board, you can summarize it for an engineer, and it will understand the implications you want to drag out of your data naturally for you. And then politics at the end. Democracy of technology is important. There are already multiple barriers for startups and early stage companies into the market. We know that funding investment, particularly in the UK and Europe, is very tough. US is very different. You can get a lot of money for a logo in California. It's very hard to get funding in Europe. Education and recruitment, exactly what Rob said before, finding enough engineers is always really difficult. Training those engineers and retaining them is very, very difficult. And protectionism, big companies have already got market holes. We know that most startups end up either disappearing or being acquired by large multinationals. And whether you get bought or you get destroyed by a company can vary on how you get. And we don't want to let the EDA company's adoption of AI and the new modern techniques be a barrier financially for smaller or startup companies being involved. So final thoughts. So I'm getting to the end, you'll be glad to know. AI won't replace people. Cost-sensitive companies will try. Strong advice is do not work for that company. If you see that happening, they're probably on their way out anyway. Ambitious companies, as always, will accelerate and innovate yet again. We've seen it time and time again. The good companies, the newer, smarter companies have adopted form, they've adopted constrained RAM, they've adopted all these things. And what's happened is we either expect to get a higher quality of a verification. We do see this. You look at Harry Foster's data, we have more right first time silicon than we've ever had before, despite the fact that designs are 10, 20, 50 times bigger than they were 10 years ago. All timescales will shrink. We'll either get time to market or we'll raise the quality of verification. It's a new hammer. Again, if you can't see, hammers with AI on it. AI will and should change how we work. Syntax becomes almost irrelevant. Code is code. If you don't know how to do it, it will tell you how to do it now. The real thing is explaining what you intend to do concisely and letting it help you do it. And I think this is how people who have always been good at coding have understood it anyway. If you can generally code in C or Python, you can code in pretty much any language. The syntax doesn't matter. It's the intent. It's how you organize the data. It's how you organize your structure of code. But don't expect EDA to do this for it. They'll provide tools, they'll provide things to help, but that's just good engineering. They will not be able to help you on that. Semiconductor industry is too small to be insular. I know we all work for massive, or most people work for massive companies worth millions or billions, even trillions of dollars, but it's still a very, very small industry. If we compare ourselves to the big software guys, the software code base available online is colossal. And it's all being used to train large language models at the moment. People are reading it in all the time. The quality of training on things like Python, C, HTML, JavaScript is already accelerating away from us in system parallel. So we need to embrace some of the software design styles in order to stay relevant. Embracing change is as dangerous as ignoring it. Again, if you haven't tried this, there was an article on the internet a couple of days ago about a lady that accidentally had a bug in her code and spent $70,000 on cloud-based machine learning in 3 minutes. That can easily happen. If you haven't got limits on it, it can easily happen. So you have to be aware of what benefit you're getting from adopting new technologies when you pay it into how much you're spending. Like, it's very easy to spend a lot of money on stuff that doesn't actually benefit what you're looking for. Again, this is just my personal thing. I say that all the time. Avoid defensive creep and FOMO. One of the reasons my old boss Holger at Cirrus always asked me, why does verification take longer and more people than it used to take? And the reason is because we keep adding things in to do it. We add form, we add connectivity checks, we add always. People forget you've got to sometimes remove the stuff that we used to do, which has been replaced by better ideas. We can't just keep adding things in. We have to see what value they add. Trust but verify. I think actually the next 3 to 5 years is a really dangerous time for the industry. It's a really exciting, seemingly very capable technology. And anyone that's done it, AI can produce results way beyond what you expect to do. You put something make me a FIFO into ChatGPT. You'll be amazed. It generates you a pretty much perfect FIFO, well commented. It works brilliant. It can also produce results that are incredibly infuriating and really unbelievable to understand. A friend of mine once described it like when you get into a loop, it's like arguing with a 3-year-old. You can't convince it that it's wrong, and you can't explain to it how wrong it is. So you have to be really careful. It doesn't do it for you. And if you start getting lazy and thinking that just chucking it into an LLM and getting the results out, we will we will undoubtedly make a colossal cock up in the next couple of years because somebody has trusted something that they shouldn't have trusted and it's leaked into code base. And this is only a good thing for verification people, particularly. It doesn't change what we're attempting to do. It's just an extra risk. I only had one right to press. It's an enjoyable challenge. We've been through this before. There's loads of opportunity to do this really well coming up over the next couple of years. And we need to embrace it and choose how we're adapting to it because there's going to be a lot of opportunity to do things well in the future. I think that's my final slide.
Excellent talk, Andrew. So the question to you, a lot of what you're saying is what it can do for us in the future. You are using it right now. So whether it's OpenAI or DeepSeek, whatever you want to choose. On the design side, and you compare it to the verification side, how much more productive are you now than you were a year ago if you weren't using this?
So I think it's hard to quantify. So it's personally over the last year, I've gone from I almost never Google anything anymore. you can put it into ChatGPT or DeepSeek, whichever your favorite one is, and you'll get a more customized result. So on a daily basis, the search time and the iterations around figuring out a syntax, a weird piece of code that personally I forget the fork join of System Verilog every time I write it. I know I've done it 50,000 times, and I always forget if it's got a begin end or a semicolon on the end of it. So that kind of thing has improved it massively. I think it's incremental. I think the project we're seeing at Accelerate at the moment, most of the design was done before people started using co-pilots, but we are seeing it begin to creep in. Part of this has been our own resistance to risk. So we are a pre-profit startup until we have a private cloud for AI. We can't send it to an open sourced company that's then saving that data and using it for its training. And that's when really the productivity begins to come in. But you can start using that on your code base. And one of the things we've only just recently started doing is loading all our internal documentation into a large language model so that people can ask questions to our internal design. You can ask about our design standards. You can ask about our design data sheets and get the answer straight away. People don't have to know what to search. But I think personally, I've seen it improving quite to the point where I use it constantly myself. In terms of getting the team adoption, we're not there yet. I imagine it will happen over the next year. You tend to see the same things. The people that want to use this are the people that were already very code savvy. They were the ones that were already using highlighting on their coding. The guys that were already very good at figuring out how to search data for themselves, they're the ones that are pushing ahead and taking the best advantage of this. Encouraging that to trickle down so that everyone in the company using it is going to be a challenge.
Interesting. So one very contentious question, given where we are with System Verilog and the fact that most of it's locked away from the benefits of AI-driven AI creation, is it time to move to, let's say, a TypeScript-driven world or Python-driven world?
I think there's an opportunity there. So the benefits of UVM, everyone knows about. So it made hiring a lot easier. It makes training a lot easier. You can pick up VIP. And the main thing for me was it introduced a methodology. Everyone understands what a driver is, understands what a sequence is, and they understand the idea of phasing and stuff. You can now go with Verilog and CocoaDB, and you can do a lot of work with that. Can you take out a full mass production chip with it? Probably not yet. No one would trust it that much. I think all the EDA vendors have started supporting CocoaDB in that more Python-based world. I think we'll see that come in more and more over the coming years. Because it's a richer language, because also the kind of designs certainly the larger designs we're doing, the maths libraries you get in things like Python, the encryption libraries you get in Python, they save so much time. I know you can do it through PLI, I know you can do it through DPI, and you can call C code, but when it's just there and it just works and you just have to import a library, I think we will see people adopting it.
Thanks.
Thanks, Sean. Any other questions? No? Any online, Charles?
Nope.
No? Okay. Yeah.
You floored them.
Hi, thank you very much. Next up was Bruno. Bruno Jansen recently joined IMEC as Regional Managing Director of IMEC UK and Site Manager of IMEC Cambridge UK. He's focused on growing the IMEC Cambridge UK team and exploring collaboration opportunities across the UK. He's worked at Motorola, ARM in positions of design of 3G chipsets and CPU verification engineer. Bruno, welcome.
Hi.
Bruno.
It's interesting, isn't it? Because I've worked for ARM for a number of years, 18 years, and I've done verification. So the last two presentations sort of really resonate with me. So I did work for ARM for 18 years. After that, I worked for a startup for 2 years looking at AI, particularly that was a company doing some optimization on AI models. So I've been with IMEC for about 4 months. And oops. So I'll start by talking about IMEC a little bit, because I think it's not familiar. People don't know we have IMEC as a presence in the UK, and I'll come back to that. So why IMEC? IMEC has been around for 40 years. 40 years, particularly looking at technology scaling. What's specific about IMEC? It's the ability, the capital investment has been very important because we are one of the few research institutes in the world that has maintained this level of capital investment. To do what we do, we need to be able to afford ASML equipment. And there's been a number of companies, a number of research institutes that went that way. And not many are left. Because if you want to know what's happening in a fab, many fabs keep the data themselves. Because we research institute are interested to make the data public. We work like a university. So what is why IMEC? We sit in between the sort of corporate world and the sort of academic world. But ultimately, we really want that data to be available. So IMEC has grown to be over 6,000 employees. Our revenue is close to €1 billion. So a couple of things. So our clean room. So this is where we are today. We got so we got three clean rooms. This is our 300 millimeter clean room that so I'll talk about the academic excellence, because IMEC has existed because of its ability to create link between government and industry. And we work with over 200 universities in the world. So the reason we So we expanded internationally, and we created a new entity in Cambridge, particularly because we want to benefit from specifically from everything we can leverage in UK. Cambridge UK has been in existence for over 2 years. So we started off with five engineers from ARM, and the company has grown. We got now about 13 people. And one important milestone was the creation of a legal entity in May last year. That was a milestone. And the reason for that is we want to grow. We want to exist in the UK. And we started our first funding project, which was about slightly over a year ago. So now let me explain our mission. So there's almost 2 pillars to that mission. The first one is we want to recruit. We want an ability to lead and leverage a number of global programs. So we got the NEST CCO program, DTCO program. And the reason those programs make sense is because we can scale those programs globally. I mean, the research we're doing here in UK for those programs we could do in any location, but we think it's really important to leverage the sort of resource we can find in UK, because if you think of Leuven, there's only so many people, so many resources we can find in Leuven. But being in UK, we can actually leverage a much wider pool of resources. The second angle to our presence in the UK is to enable collaboration. We want to leverage everything the UK has to offer. Particularly, we want to look at doing research, leveraging anything we can do with academia in the UK. There are many companies we want to work with, particularly UK is particularly strong on fabless, and there's many more angles we can leverage. IMEC has a very strong history of supporting startups, and being in UK, I think we can do that. We can do that better. So I'm going to say a couple of things about IMEC technology roadmap. So IMEC has been driving the technology roadmap for over 40 years. And the truth is we will continue to drive that technology roadmap for the coming decades. So let me say a couple of things about the roadmap. So this is our roadmap. If you look where we stand today, the production is around 2 to 3 nanometers, so FinFET is in production. We've done a lot of research on nanosheets. We produce PDKs. Our PDKs are pathfinding PDKs are widely used across the industry, and we're starting to develop those for the next generation. So if you look at the roadmap, you see nanosheet, forksheet, CFET, and this is scaling roadmap. We think we can continue to scale that roadmap for another 10 years. But one thing that we realize that we got a problem with density, because as we continue to progress the different elements of the transistor architecture, we still have a density problem. It's harder to scale. It's harder to achieve the density, and we see we think some boundary with what we can achieve. So I think another element, because if you think about IMEC in terms of research institute, actually the work we do is helping research. So we develop a number of roadmaps. So we talked about scaling roadmap. The memory roadmap is really important. So if you look here, if you look at this graph, SRAM is very important. It's really important for sort of on-chip design. If you look at the sort of memory middle, DRAM is going to be off-chip, and then you get into storage. So I explained the density problem. Density problems having an impact on SRAM, which means that as you go down, as you go to next node, you can't really scale. You can't continue to scale your memory. So this is why we're starting to research different type of memory. So on this one, we looked at M1, STT-M1, and going into SOT, so magnetic ones. And we talk about alternative. I mean, that's been a key subject of presentation before. Serial integration is very important. We talk about 3D, we talk about chiplets. A couple of illustrations here would be, you could have a 2.5D integration of DRAM. You could have a processor integration with typically you could have a 3D integrated non-volatile memory on top of that. So I'm going to talk about hardware software co-design. So first, the objective, I mean, we continue to look for increased performance, increased complexity, reducing cost, reducing power. I mean, those goals are always the same. And I want to talk specifically about what we're doing at the Cambridge site. Because if you look at the history of how we've been looking at systems, typically you started at the application level, where you wanted to look at software level, you would optimize a piece of software to a target device. So, but what we want to, the way we look at system moving forward is, we think it's important to look at all the elements of the stack. And being IMEC, we're looking at the sort of basic underlying technology. So I talked about the different roadmap we provide. The CMOS scaling roadmap, memory roadmap, we've got an optical I/O roadmap, and how we connect them together actually the value that we can bring. So to describe STCO in different terms, so what we call system technology optimization is the ability to do that situation between technology. So what I meant, when I talks about technology, we talk about this sort of underlying semiconductor technology. So what I mentioned, so the scaling roadmap, the memory roadmap, and we look at combining those technology to what we can do at the system level. Because what we learn from the system is something that's going to influence the way we look at the roadmap. So, and it works the other way around, because when we discover something about the underlying technology, that also feeds about how we design the different system. And this is an illustration of how we can look at system differently. And this is actually something really new for IMEX that our team started a couple of years ago. We start to look at different systems, and we start to look for that particular system, which technology are relevant. So on this one, we talked about 3D partitioning, active interconnect, function backside, and optical interposer. And they all have a different meaning. For example, if you look at the sort of data centers, the sort of optical interposer is going to be important. We're going to look at accelerating the data between the different parts of design. We're also looking at 3D partitioning and how you can, for example, on a mobile system, combine non-volatile memory and 3D partitioning. This is what we mentioned before. 3D is becoming important. I mean, we talked about it, when we look at the sort of chiplet design, and a combination of a CPU, 3D partitioning to bring memory is something we're looking into. So, a couple of illustration of, what it could mean and how we map the sort of system to the particular type of technology. Now I want to talk about this project, particularly the XMAS project, because that's a really good illustration of it's an open source program that we started about 6 months ago, which is doing exactly that. Open source because we can map all the different elements of the system. So we start by looking at possible system. So that program is particularly looking at AI training to reduce the cost. So if you look at AI training as a workload, we want to be able to reduce the cost of that by by a significant magnitude. So why is it an open source framework? Because we can map different systems. So you start at the software level, so you look at the workload, particularly you would take a typical AI workload like it could be ResNet or Llama 2. We can extract sort of basic function, basic instruction, and bring those at the system. So at the system, we can model different architecture. You can have a GPU architecture, you can have accelerators, and our model would bring it down to the next level. Because if you go one level down, you can start to map the way your system is organized. So the way memory are going to be structured, the way the different components are going to be associated. And down the line, we also associate a cost function. So when we look at a particular system, we're going to look we're integrating the sort of software element, but also trying to organize to understand the cost, the overall cost of ownership associated with the system. So it's a project we started. It's got a long way to go, but because that program is open source, it could be shared and it could be made available to the wider community. So working with Cambridge UK, we got a wide selection of technology and research of interest. We talked about system technology optimization. This is the main interest, the main focus of the group. But we're also looking at collaborating with different parts of the UK. Particularly, we want to work with academia around projects that involve memory research. We're looking at 3D integration advanced packaging. We're also looking at collaboration on silicon photonics. Also, we want to leverage compound. Compound semiconductor is a very strong area of research in UK, particularly because we base in London and we don't benefit from all the academic network we got in UK. That's something we want to leverage, particularly for advanced RF and power electronics. And I mentioned AI workload because through the SCCO program, we started to look at all the different layers. And when we build a system, and it's becoming much more important to understand what AI does, particularly, and there's a very important part of IMEX that's actually studying AI and AI algorithms. So understanding studying AI workload in the future is going to be very important for IMEX. Okay.
Any questions? Okay, so,
Is there anything IMEC is doing on the academic side of things to help universities improve their syllabus with the way they're teaching semiconductor design or semiconductor manufacturing?
It's just a fire test.
Great timing. Like for example, coming from the university side with the way they're teaching things nowadays, for example, for Andrew, you mentioned in your earlier presentation that you learned constrained random testing in university. I didn't get to learn that until I stepped into the real world. So there's a gap between university and industry, and I'm wondering what kind of collaborations is going on between IMEC and local universities in the UK in that aspect?
It's sort of about, I think there are two angles to that question. The first one is, IMEC's got a very vast network of, relationship with university. We have a high number of PhDs, so we keep the link between the university and IMEC. Multiple programs. Those are very well established in Leuven, and we try to replicate this model in different geographies. The other one, something we like to develop is anything to do around training. I think training is important. We don't think there's any sufficient training available, so we'd like to leverage any program that could, ensure we can teach what we know. If you look at IMEC inside, IMEC actually got a very fast full of information. The information inside IMEC that we have available is actually hugely valuable. I think there's an element we could leverage, the knowledge we have inside to either make it available again. We're a research institute, that's what we do, but particularly in relation to how we work with universities.
Any more questions? There's none online. I think we can finish there, Julie.
No, I'm happy. Bruno. Thank you. Next up is Paul, an ex-colleague of mine. So Paul's a business development manager at the CSA Catapult. He worked at NEC Semiconductors and Product Engineering for DRAM memory devices, followed by 3 years at NXP Semiconductors. He joined TechWorks in 2005 and led the electronic product design, test and power electronics networks for over 7 years. He then became the director of DESN, which is one of our networks, the Automotive Electronic System Innovation Network, in 2015, engaging across the automotive electronic supply chain while co-chairing SEMI-GAAC. He's now business development manager for the packaging centre at CSA Catapult in South Wales, and also centre lead for Driving the Electric Revolution Industrial Centre South West and Wales. Welcome, Paul.
Thank you. Good morning. Delighted to be here. Thank you, TechWorks, for inviting me here. I'm standing in for my colleague, Jay Chandrahan, who was going to give this talk, who's ill. He gives his apologies. Competition. Yes, okay. So you probably looked at that slide long enough. So talking about from chip to systems, redefining semiconductor packaging and integration. Hopefully from what we've heard already this morning, packaging is starting to play a more central role as we move forward to more complex and highly integrated systems. I will explain what the Catapult does just a little bit as we go through who we are, but just really setting the scene here. First of all, it's a changing trend. We used to read books. We used to, sit together as families. We probably look more like this. I don't know if that's for people here, but certainly for me, we've all got our own sort of device here. We're all really tapped in, and what the area we're in here really this sort of connected, always connected, and hopefully safely connected. So we're in this era here. Where are we going? And I think we heard quite a lot of exciting topics this morning already. AI-based systems are helping us get into more automation, reducing the speed that reducing the time that we take, moving more quickly. Quantum technologies, quantum computing comes. So we're going to a new era, very exciting from what I heard this morning. So advanced hybrid semiconductor integration and the next generation of hardware needs to go with that. Again, just sort of scene setting here. What are the things driving this? Okay, so we're over here. So you get connectivity. So we all complain if the internet speed's low. Certainly my family do to me if there's some problem with their internet connection. Cloud computing versus edge computing. Okay, cloud seems a great solution. Is it the solution? And maybe looking at edge computing and the trade-offs that come between those. Secure data, TechWorks run its own network around this on security. Extremely important to make sure that we're safely connected and understand the impact of not getting security right. And at the end here, digital transformation, AI integration and cost. Like we mentioned here, there is a trade-off. It's not for free always, and we have got a lot of skill and technology that we need to get our heads around. Okay, so with those challenges, sorry, a bit of a busy slide here, but what this does, and we've heard a little bit of this already this morning. If you look up in the top corner here, Moore's trusty law here, or trend, whatever you want to call it, has stood as well up into the 2000s. But if you start looking at it here, it does start to roll off as we get into this of smaller transistor density here. So increasing that and taking that, continuing down that route is clearly difficult. Over at the right here, I think this was mentioned as well, 40 nanometer. Yeah, these are just rough figures, 100-person years, and then at 7 nanometers, and who knows at 3 nanometers, 2 nanometers, we heard, yeah, you're probably looking at some pretty heavy amounts of resource there. Design costs down into here. If you look in here at these, so for reuse, so reuse for design becomes key, and we've heard that already this morning. You're looking here at these costs, this is in dollars, but $1 million, 65. You get some pretty eye-watering numbers here to develop chips at these nodes. So clearly that's going to drive us into what are the other options. And then over here, we've heard already, interconnection speed between chips. So die to die speed, this sort of 4.8 terabyte here, and package to package, obviously quite a difference. So look at multiple dies, one package that drives that kind of look towards what we're calling 2.5 or 3, maybe 3.5D high density integration. So this is kind of driving all of what we're doing here. A really good example of that, and something we do quite a bit of focus on with our new hub at CSA Catapult, is looking at optoelectronic devices that are powering telecommunication systems of the future. So high-speed data transfer, robust global telecommunications, and these devices that now we're calling PICs, or photonics integrated circuits. So harnessing the ability to drive that data and looking at sort of cloud data servers, and where there's a lot of energy being used to store and transmit the data that we have today. So one of the big sort of topics we're sort of looking at here, sorry, that seems to have written over there. So optoelectronic devices. So just giving us an example of, what are these devices that we're talking about, what the device technologies that we look at Compound Semiconductor Application Catapult. Look at light sources here, so it's a bit dark. Light sources, light control, and light detection. A range of these devices, laser diodes, vertical cavity, surface emitting pixels, LEDs, looking at how we're managing that, how we're controlling it, and then photodiodes, so it's all in the sensing side of the light. The point here is that this diverse set of materials, silicon plays an important part. And although we had another version this morning from ARM, from Rob on the CSA, but certainly from CSA, from our side, Compound Semiconductor, we're seeing ever more requirements to bring together silicon, which plays a continuing important role as it goes either to smaller nodes or in this control function combined with compound semiconductors. This slide here is just showing compound semiconductors in this diverse range of where they appear and some of the things that we work on. Today, I'm not really going to talk much on power, but from a power point of view, obviously looking at silicon carbide, gallium nitride, these materials are now becoming very widely adopted, particularly in electric cars, where you've got the ability to have far more power efficiency, and we can drive things at 800 volts. And now we're seeing silicon carbide devices going up to 2,000 and 3,000 volts. So switching very high voltages. We'll look over at the side here, RF. I'm talking a bit more on RF and photonics here, and a bit on the LEDs and optics. A whole range of technologies appearing in all of these applications. So from your mobile phone and how it can tell that it's you and it illuminates you with laser. Telecoms, absolutely at the centre of telecoms and sensing around vehicles, connecting of vehicles being connected and talking to each other, which is going to be an interesting era that we move into. And how do we know that data that your car is sending my car I can trust? And then you see a whole range of materials here down into medical, wearable, and I'm not going to repeat what we've already heard this morning. So a huge range of areas where these materials are appearing. And with that, we need to think about silicon photonics. I mentioned here about PICs and new functionalities and how we're bringing those together. So this is really the area where packaging comes in. Typically looking at it in a very rough sense, two sort of ways to look at this hybrid integration here. So you've got, as we heard earlier this morning, this is a VCSEL example here, solder paste example. So you've got that on here, fully processed chips there, but hybrid connections onto that substrate. We'll talk a little bit more about interposers that play their part in between the 2.5, 3D. This side here, I think what we're hearing from IMEC, Bruno, we're talking here about films, just an example of lasers and the sort of advanced laser technologies being processed at wafer level or encapsulated even at wafer level. So this kind of strategy here, heterogeneous integrated versus hybrid, the way that these technologies are now developing, the way that they run side by side into the future is now where we're putting a lot of focus. So we need to understand when is it right to start looking at post-fab or pre-processed wafers. When is it right that we just look here at how do we integrate more of those devices onto one package? Apologies for people at the back. This is probably getting increasingly difficult. I'm not going to talk through these in too much detail, but today where we are, if we look at optics here, so just an example of optic devices, a transceiver here on the board. Typically the challenge that we've got here is that the electrical path between this pluggable module here and what we're doing to control that is meaning that there's no way that we can take advantage of the speed at which we would like that to operate. As we start to bring those devices together and more sort of on-board design, we can improve that speed. And you're seeing here examples of just the improvements here. So you've got the energy level coming down 20 petajoules there. You look at the speed here, sort of quite a significant increase in speed. Ultimately, where we're going to this term of co-packaging or co-packaged optics, you're getting massive improvements here in terms of speed and reduction in power. This is all, there is trade-offs in here, but ultimately as a goal, you're looking at reducing that E-path, but signal integrity bandwidth and power all will benefit. So there's a big goal to play for here. So this sort of optical engine, as we call it, and the ASIC and the control devices existing together, coexisting. So that's a big part of what we focus on, a lot of the research work that we're doing at the moment. Again, sorry, just a little bit small print here, but ultimately what I'm trying to just show here is there's sort of on the left here, what we've got is this a whole list up of all the variety of different types of advanced packaging. So you've got traditionally sort of side by side here, what you typically see is a chip and a photonics chip connected together. Here at 2.5, we've got the interposer. So the interposer acts as an area where we can have a pitch that's not quite as fine and refined as we would have in the wafer fab. There's something we can manage on a substrate. And then we go up into here into flip chip, so basically stacking the devices. We've got these micro bumps, micro pillars, and again, we start to get challenged with the pitch of some of those. Then we're down here into 3D stacking, so you get through silicon vias and ultimately monolithic. So if we could do it all in the fab, we could run this through Bruno's IMEC fab and have the full device here, it'd be fantastic. Ultimately, what we know is we're probably sitting in some solution here. The reason for that is if you look at the trade-offs here in connection, floor planning, complexity, we've had a lot of these this morning, reuse, thermal management is huge, interconnect and parasitics and complexity of the design and verification. There's a big amount of trade-off to consider in here. A big part of what we look at CSA is working out how are we going to work out the optimal solution. This is where AI starts to come into play. We use multi-objective optimization, MOVE's our acronym, an example of that already doing in the case of power electronics. So we need to bring the power that AI can bring us to compute that in what would typically take you maybe 6 months into maybe more like a day. So that's an important part of understanding what is the right selection, what is the right choice of what we do here in the packaging. understanding these trade-offs. Okay, just a little bit about the catapult. I'm not to do too big a sales job, but I've always warned people off in that in the past. These networks. But anyway, who are we? So CSA Catapult, government funded, part of the Catapult network. We're here as developing and commercializing new complex semiconductor applications. So we're not really spending so much time on the chip. We're looking at what we can do with that chip to take it to an application. We work in a range of ways with industry to support you. 110 million funding over 10 years, established in 2018, headquarters down in Newport in Wales, and over 100 staff. So looking at what we cover here, power electronics, photonics, RF, and advanced packaging. So today we're also focused here. You can see that we cover right across that whole range of technologies. So some pictures here. I'm just going to maybe a little bit more, particularly focus on packaging. So what we have in the sort of main centre in Newport, you can see here we've got a range of capability. We've got two sort of clean rooms that you're seeing in the picture here. Just seeing maybe. So we've got a traditional packaging line here, which has now been running for several years. We've got a new 3D additive ceramic metal printing capability that's just been added. And this is linked into the funding that we received from Innovate UK through the DER programme, and linking now into the work that we're doing on scale up with NMS at the University of Strathclyde in Scotland. Importantly to say, and I think what we've been hearing today, and I wouldn't dare to try and repeat in detail the tools that we have after this morning's talks, but really the importance of this co-design. Traditionally, the way that chips would be designed and handed to a packaging house is broken. And if you think about co-design, it's important from the way that packaging is now changing, is that we need to understand right up at the part here what's going on in the fab. We need to understand the limitations of the wafer fab and what post-fab processes can be done, and then feed that into a design and bring it right through into prototyping and small numbers of samples. So we can produce those prototypes, we can do 5, 10, 20 pieces, and we do that regularly in a range of projects. So package design, assembly and testing, and a whole range of things that we need to understand about reliability. We need to understand how these parts will actually work in an application. Hybridization, just stopping for a moment here, but this kind of equipment, we're talking about highly capital expensive, big investments been done here into sort of sub-micron placement. Here it's shown for photonics with very fine pitch bumps here. It's important we start to develop these projects. You've got some partners we're working with here and have that capability here. Traditionally, a lot of this has been going offshore, OSAT particularly, but bringing more of that capability back into our own backyard. An example here, what's happened up there, so I'm back. An example up here, and working with partners like IMEC on a lot of these technologies now. Traditionally, there's a 2-to-1 ratio here in the size of the ball, basically, and the pitch. But what we're moving towards is looking at this at 10 micron, even down into sort of 6 micron bump. But particularly going to photonics, we're going to very highly dense devices that we want to bring together. We're moving to really the edges of what's capable in traditional packaging. So you're looking at very much for something that, probably when we're down at this end of things, get below 5 micron, you're looking back to the wafer fab to see how you can work between the back end and the post-process of the fab and what we do in the packaging line. Okay, so just showing a little bit more on this. So I mentioned here about 3D packaging. Then packaging, people here that can argue with me. 3D relatively new in terms of packaging from an additive perspective. We hear a lot about 3D integration. We're looking at the use of these materials and additive processes to almost get to packageless packaging, where we're embedding the devices. We're looking at ways in which we can massively improve thermal performance. So multi-ceramic materials allow us to get the chip directly or nearer to the heat sink. I'm just showing here there's quite a bit of post-processing required in here that goes along with that. But just an example here, just like an example, okay, what is 3D? What can you do? So you've got some examples here of what some multi-material substrates could look like here. And in this process, this typically periodic minimal surface application of that kind of technology, you get sort of maximum sort of flow, you get maximum thermal and surface here. And you look at something like here, here's an example of a you know, a heat sink for a coolant flow through here, device with the setting on top. So traditional sort of cooling, Wakefield cooling system here, and then mass. Okay, so you're looking at mass, so we're considerably lighter if we use things like alumina, but the heat transfer here is 14,000 versus 6,000, and a sort of smaller footprint. So massive improvements in thermal performance. So we're expecting to sort of use this more. It isn't cheaper. 3D printing isn't a cheaper solution, but when you look at what we've discussed today, system performance starts to become key, and then you understand how that's going to impact our sort of thermal resistance, inductances, parasitics, but very much big improvement in thermal. So just another couple of examples here, just to sort of show what we'll be working on. This one here, we've got a sort of RF GaN application here, as a MIMIC type device, microwave. And you're looking here, so in this case, direct bonded copper, but you get diamond heat in here. So diamond heat expresses diamonds, best thermal conductor that we know of. So how we're sort of working with those materials to improve our capability to work in the areas where we're either short for space or for cooling, or we want to reduce cost. A lot of these also looking at application space, areas with very harsh environment. 6G systems, so this kind of term hyperconvergence. So what you're sort of seeing here is, it's been mentioned on the talks already this morning. You're sort of looking at a range of heterogeneous, if you like, really different types of technologies appearing on here. In order to sort of optimize this range of technologies that are on here, you get multiple technologies ending up in a sort of single package, particularly on future generations of sort of lower power requirements on 6G. So sort of looking at how we can combine those systems and make them perform at these kind of speeds, but not have the same power requirement. Okay, just sort of wrapping up. Really what I started off the talk talking about here, and sorry, these have gone a wee bit hard to read, sorry. But effectively what we're looking at here is sort of looking at the new approach to packaging, if you like, really. So a heterogeneous hybrid integration, adding value and refining the complete process. So if you look at this picture here, you've got some advanced packaging processes here. And traditionally, if you looked at this, certainly when I started looking at semiconductors, packaging was something bolted on the back of what was a lot of the start of the chip design right through to the package. Today, it plays something much more of a central sort of hub and spoke. And what you're seeing here is the chip design on the left and this advanced package design, this hyperconvergence will only work where we understand how to do that design, co-design together. So a lot of the tools that developed here getting much closer and integrated with tools across a whole range of these different device types and technologies that wouldn't generally have found themselves sitting side by side. So you've got here semiconductor chip design and manufacturing coming together. Go through this process and some of the things that Bruno mentioned there about different initiatives to standardize these things. Obviously some really good examples this morning. How we sort of look at optimizing those processes, we will absolutely rely on the application of AI learning, all of the technologies that we can get our hands on to get out here to application of devices that are actually more efficient, that can offer us more performance. Added this bit in here, and it usually ends up with the people, the engineers that are the packaging and at the back end of the process. The reliability goes wrong in the field. So we're trying to find out what's going on and contain that problem, and it could be in a car, it could be in a plane, hopefully not. But whatever that is, a bit like the cyber problem, we've not focused on that today. We need to be able to understand how to track that back. So these processes need to be very much aligned, they need to be very much co-designed in the methodology. And I would say that the skills, which Stu's here today, the skills that we require going forward, and UKSF doing a fantastic job of helping us bring the right skills to the community. They're going to be multidisciplinary. They're going to be learning about a lot more in materials and learn a lot more about thermal, a lot more things that the engineers would never have looked at in the past. So this is the model we're bringing forward, and give credit to Jay, who's brought this slide to us today. But I'd love to talk to anyone today, like to know more about what we're developing in here. Fantastic to see the turnout that's here today. Thank you to the team at TechWatch. So thank you.
Hi, Paul. It's actually a question that might be even talked back to Andrew, because I thought you made a great point there in your last point about the field analysis and reliability. Does that feedback ever go back to as far as the design verification process to improve coverage?
Yeah, I mean, particularly as the chips are getting bigger, and especially the chiplet designs, ECC, error recovery, the high-speed interfaces now, the forward error correction on the high-speed interfaces is important. It's actually quite a big chunk of the design now, and particularly if you're doing performance, you have to equate into it whether you have an ECC error in order to recover in time not to make a change. It's added a lot of space into the verification.
Hi, sorry, Paul. I'm going to ask quite a big question of actually Rob and Andrew and you together. Obviously, thinking about chiplets, advanced packaging, what I find really interesting is how we bring different substrates and functionalities together, like photonics, electronics, translation from light to electronics and back again, maybe via the interposer, the interconnect. Open question to anyone who wants to talk a little bit about, is there a role to play for automation in the way that we can think about developing an integrated system at that level using, as I say, photonics, electronics, and so on in a complex integrated package?
Yes.
Any more?
Yeah, I mean, I think the reality is none of this works if it's in isolation, right? So I think the point is that more than ever, the sort of concept design for manufacture, EFX or whatever terminology you want to use, kicks in here, right? Because the impact will be seen and it's too late to go back and start the design. So there's various sort of things, initiatives on chiplets, IMEX to its own. There's various things kicking off, and I think it's a great opportunity for this forum, what you're doing here to sort of bring that together. So I'm very keen to work with all the initiatives that have been on. Yeah, I think the answer is yes. We did it in Europe. There are several initiatives kicking off around that as well. And Julie mentioned STEM. So yeah, I think there's a real need to sort of bring together the communities. EDA is served as well in its sense of what it's been. Certainly for automotive, the standards they've got in design verification massively years ago. So there's more real-time systems and all the updates, all those things. Yeah, so I don't know that. Easy answer.
It's a difficult question, but yeah, no, thank you.
So I'll give a plug to some stuff Mike's doing because he's helping write some white papers on this. But I think probably the physicists are further ahead than everyone else on how to actually integrate this. The DFT, the verification, the protocol standards, the data movement is probably very infant on this at the moment. To be honest, we're not very good even at things like PCIe. It's a miracle it works in many cases.
There's something you said earlier which resonated with me. The last time I designed a chip system, we probably had 3 or 4 R-class ARM microprocessors in an SoC, some accelerator hardware and an RF front end, and we had to boot up to the RTOS and run real protocol code, and that probably took a couple of days on an accelerated box, right? You're talking about running AI models on multiple NPUs. That's a whole other ballgame, right?
Yeah, the scales, we don't have the scale there at the moment. That's something we have to make into now.
Yeah.
And I think one of the things we're doing, I think a lot of companies are doing, we're building new systems, and we're doing everything electrically that we think will make sense. We're using IPs and we're taking best practices to ensure that we get the right solution. But we're probably where we were in verification 20 years ago on SoC design of how confident we are that everything's been caught. And fortunately, there's been a lot of really good stuff in the process and the packaging to mean that we're actually pretty good at this. But proving it as it gets more and more critical that this is how good chips get designed, is going to be a big step forward in the next few years.
I'll just follow up with one point Andy made as well. We are producing some white papers for the OCP, if you've heard of the OCP, which is the Open chip project, which is doing a lot of work in chiplets and UCIe. And we are writing white papers, one on testability of systems built from chiplets, and one is the verification of systems built from chiplets as well. So if you're interested in verification of chiplet-based systems or testing of chiplet-based systems, then let me know. Okay. Any more? I can't see any more hands up. Any online? No. Nothing online. Okay, I think coffee back in somewhere.
Yep.
Yeah. I hand back to Jim.
Coffee served. SatishKumar B, who is a Senior Director of Product Management, Marketing and Business Development at Siemens. He's an experienced product leader with over 20 years experience in the EDA industry. Currently leads the product management and marketing organisation for Slido Custom IC division and AI initiatives at Siemens. He holds various product management, strategic business development and corporate development roles for Cadence Design Systems and Synopsys School of Business. Welcome.
So I'm the last EDA vendor here, so there's going to be some repetition, but it's interesting to see how we all say the same message in a different way. So what I want to talk about on terms of unlocking AI advantage with Siemens EDA products, I've been in Siemens for the last 10 years, and right now for the last couple of years, I'm leading the AI initiative for Siemens EDA from a product perspective. So I have some insights on what we're doing. So feel free to interrupt me for any questions. So the challenges are always the same, right? The design volume is increasing. That's just 1 trillion already been done, already been said. Complexity is exploding. Costs schedule are skyrocketing. According to the latest reports, it's close to around 320 to 400 million in terms of designing the latest chips, right? So the stakes are quite high. So we can't make a mistake in terms of EDA software. The talent shortage, we've been talking about it. Everyone has talked about it. So just for US alone, for the next couple of years, it's going to be about 40,000 engineers talent shortage. So all these are definitely focused on design productivity. If you look at the chart over there, as we are moving from one across the process nodes from all the way to 2 nanometer, the amount of effort or amendments required across all different prototyping, verification, and software, the man was required is actually increasing. So this is definitely, it's interesting because the time to market is actually shrinking, whereas the challenges or the amount of hours you need to get a chip out to make it work actually is going the other direction. So what we've been doing in EDA, it's been discussed, right? We've been investing in EDA as first form to make sure that we have automation. We've been figuring out new tools, new methodologies to bring in better automation, verification techniques. That was a great session from you. So definitely coming up with new verification. A lot more in terms of design reuse, like hierarchical design and so forth, that's been happening. And employee training and development is happening, and collaborating with a lot of research like IMEC and every other institutions in the world. So we view AI as another way for us to, at Siemens, to actually help you with your productivity challenge, right? That's how we are viewing AI. It's another I would say, a methodology or a tool that, as an EDA companies, that we got to adopt to make sure that we serve you better. So I'm going to talk a little bit about production grade AI in terms of the reason why I said production grade is exactly to the question that you asked last time, right? I think just before, why we are not on the cutting edge. Before I do that, we just did on the IBS study. It was interesting for a 5 nanometer tape-out. They had a traditional flow and they had flows with AI. When I say AI, it's also ML based optimization as well. They definitely saw close to 50% on average productivity gain by using flows and methodology with AI and without AI. So one of the things that we are focusing on is to make sure that you have error-free design, it's repeatable, and comprehensive functionality testing. Right, those are the key areas that we are looking at. But the most important thing that we find from customers, from experience, is any kind of innovation we do, they still always come back to accuracy and reliability, right? They say, yeah, you can come up with a good answer using AI, but make sure that it's accurate and reliable. Like that's always been the, I would say, the more compass in terms of how we are developing software in EDA. So I'm going to talk about some key components of what we call a production grade AI. So we acquired a company in Siemens EDA, part of a company called Design Automation. I don't know whether everyone knows about it. They came up with the first ML-based algorithm to do variation about design. What this means is if you want to get into high sigma verification, you want to run, for example, for a 6 sigma, you got to run 1 trillion samples to make sure you get a confidence level. They came up with a way of a very innovative way of using ML techniques to get to the same confidence level by using very few samples. So when that thing came, right, the first question when they went to the market was, people couldn't believe it, right? They came up with a great answer, but people couldn't believe it and they didn't trust it. So then they had to go back and see how we can get the trust, right? So that pretty much forms the foundation of how we are viewing in terms of software development. So in terms of production grade AI, the first key thing is verifiability, right? I need to be able to show, or we need to be able to show the proof of work in terms of how we came to a certain optimization, certain minima, certain answer. Usability is, again, that was clearly covered by our person as well. It needs to be easy to use. You shouldn't be having a PhD person be able to run the flow. Generality is very, very important because I can't have a solution that only works for a certain low power scenario. It needs to work for across the entire spectrum of the design space. Robustness is key. I shouldn't be giving an answer today, one answer, another answer tomorrow, or the same cycle, same design at a different time. And accuracy is the most foundation for us. So these are the 5 key principles we use in terms of developing software. We call it production grade AI. So it's interesting then when we bring a software product, these are all the different levels we go through, at least within Siemens. The first one, what we call it a partially reliable AI. I've been to many conferences where it's easy for anyone to come up with, for a given scope of problem, come up with an AI-based solution very fast, right? We call it that's what we call partially reliable AI. But the problem is it gives you speed up, but sometimes you can get a wrong answer, right? So the first step takes probably an hour or days or probably weeks to come up with a solution. The level 2, what we call it a partially reliable AI, but with self-aware verification, which means that you got to have a software built in, you got to have the intelligence built in, where if you're coming up with an answer, you need to be able to actually self-verify to make sure that it covers it, it's accurate. The third one is adaptive. When we add an adaptive layer, which means that it needs to be able to be adaptable to all different design scenarios. It can't be working only for one certain configuration or this kind of design space. It needs to be across the board for whatever application you're looking for. And the last one, 4, is it needs to be reliable, accuracy, everything combined, what we call the production grade software. So any software that we provide, we need to go through these levels to make sure that the customers are kind of confident in the AI solutions that we provide. And this takes time. This is where just to go from level 2 to level 4, that takes a lot of time, a lot of experience, a lot of collaboration with the customers to get a lot of design data and everything else. But that's the way that AI solutions actually come into the market. So I won't be talking about generative AI, but we all have copilots, different scenarios. But if anyone's interested, the very good conference is an international conference for LLM aided design. Last year was a great conference. There's another one coming up. If you look at all the different LLM-based design flows, all the way from RTL generation, test bench, EDA chatbot, EDA copilot, high-level synthesis generation, security, design of documentation. There is so much research going on this particular way of using LLMs for chip design. This is a great conference. I would definitely ask everyone to go look at the proceedings if you can. But there's so much research going on that every month there's something new coming up. So we are still at the early stage in terms of how we can make this into a proper thing, but everyone is working on it. And generative design, AI design using LLM should be the future. Probably not yet right now from the EDA point of view. We're getting there with products slowly, but reliably, that's key. But definitely this is something that there's a lot of traction going on. So this is another way of looking at the life cycle. So of semiconductor, on the left side is from specification, implementation, spin off on the design side. Then you have test, package, then in service. So we have tools. I bet every other EDA vendor has the same tool to cover all these different scenarios, right? Different stages in terms of how we get the semiconductor to the market and into the field to be working. But the key thing that we are using AI is all the tools, all the AI capability that's coming into the tools is essentially to address the productivity gap. So we view from Siemens EDA, we bring AI in 3 different forms. The first one is called technology, where we have AI embedded in the tool. When I say AI, it's going to be ML or RL-based engines that's actually embedded in the tool. Processes means how you can make a very streamlined flow. So for example, take your fully entire place and route optimization flow, how we can make that much more efficient using AI. And the last one is a platform where it's essentially based on generative design. And how can we do that with better productivity gain, mainly to help your engineers much more like make one junior level engineer, like the other person said, to be a very senior engineer. And we have 3 categories of AI when we look at the AI. Analytical AI and predictive AI. Analytical AI is essentially solving a big data problem as a verification debug. That comes into that category. Predictive AI is where I use an AI or an AI ML-based algorithm or any kind of a model to actually predict an answer. In this way, I'm generating something. And generative AI is what everyone talked about it. That's where you come up with an LLM-based one where you get into more of a reasoning. Agentic is coming up, and then you pretty much have your virtual engineers, right? That's the ultimate goal, where you have one person just having like 5 virtual engineers in this team to get a tape out done. So 3 key categories: analytical, predictive, and generative. So I want to go through some of the key challenges and how we are solving it. The first one we're talking about is we're using AI to integrate systems across domains, right? In this case, cross-domain optimization. I think there's different examples previously. In this case, we are actually using an emulator and actually a sign-off power using Power Pro, where we are actually trying to. This is essentially used in the software development cycle, right? As you know, the software stack is developed using emulation as one of the key pieces. But every time an activity changes, they need to run the Power Pro or any kind of a power analysis engine, which takes a long time. So what we do is we try to do a pre-trained power model, and then we use that power model as an inference engine when the activity changes the next time. What this helps us, it actually helps us give definitely in terms of runtime advantage, but within the 5% margin of how we want to run everything from scratch, right? This is very important when you're doing an early phase in terms of prototyping or software development in your cycle, right? This is something that came up with. The second one is that 3D-IC platform. There was a question about, I think in the previous session, about what do you do in terms of how can you figure out the dependencies in a 3D-IC package. We launched a new product called Innovator 3D-IC. This is essentially a 3D-IC design space optimization platform, where you can go all the way from your package to your subblocks, right? You can do a lot of all the optimizations. It understands the entire stack so that you can actually plan from top down, right? And also get all the information that's here all the way from bottom up. And this uses a lot of AI and ML models. And so I'm on the transistor side. I'm on the analog background. So in terms of and the previous person that was placing route. So we have what we call another product called Slider Cell Optimizer. In this case, where we use ML and RL in a way that when you're designing a single cell, right, a transistor cell, like a standard cell, you need to come up with the perfect optimization cell across all different scenarios. And the best way to run it is through multiple scenarios in terms of test benches and so forth. Here we are actually trying to actually figure out what are the simulation patterns that you got to run and how you can get to the best possible in terms of layout and schematic for your cell in a least amount of simulations done to get to the best optimized final cell. And that's the solid cell optimizer. And PBTMC verifier is another one on the transistor space where you have multiple PBTs. We actually come up with, across multiple PBTs, we come up with the new way of finding out how to identify a worst case PBT, and then all the way go in and find out within the worst case PBT, what's the key, or what's your actually a target confidence level in terms of sigma. So those are the key things that we use in terms of ML-based AI. So the next one is actually, how can we come up with the PPA trade-off, right? That's one of the big challenges that we see in terms of the new tapeouts that's happening. So in this case, you got to do a deeper insights, right? And PPA trade-off is essentially about able to understand your big data problem across the entire flow from top to bottom and bottom to up. We introduced a new product, Catapult. This is a tool that we have. So Catapult AI neural network. What we did is we used a high-level synthesis engine. We worked with an open source consortium having an open source package that actually develops, it's called HLS4ML, that actually develops your neural network models. And we use Catapult to generate C++ code all the way to RT. Now, the key thing, what's the key thing is, this is essentially addressing two things. One is in terms of efficiency, how we can generate from your hardware accelerators, AI accelerators using this flow. But the second thing that really helps is most of the people who are writing neural networks, they don't know RTL, they don't even know C++. They use PyTorch, right? They use TensorFlow. So there has always been a gap between how that gets translated in an optimal way to a silicon, right? Most of the hyperscalers use this product right now. So we have a flow to actually make that happen, right? So there's actually AI and ML and reinforcement learning built in terms of how we make that happen. So this is another huge productivity gain that we have. And of course, we talked about place and route before in the previous session. Aprisa is our platform on place and route. And of course, right, with every scenarios, you have like all the way from flow plan, placement, routing, post route, everything, your complexity or number of variables increases or explodes. So essentially you have a combination of almost close to, right? And if I have to, I don't think you're able to see the screen here, but for every step, you're actually exponentially increasing the number of permutations in terms of decision-making capabilities. But we do have same case of design space optimization to get to the right point where it gives you the best PPA target, helps you meet your PPA target. So that's another one that we do for PPA trade-offs. This goes down all the way to the transistor and the bit level or cell level design. In this case, we are using AI, and we are doing a PPA analyzer for essentially in a spice abstraction for multiple parameter design, comparing one output to another output, right? In this case, you are saying that, okay, for this output and this output, what is the best combination of parameters that you need to have in your design to meet your target, right? This is what we call a PPA analyzer. And it also helps us identify the worst violators as well in terms of your parameters. So there are a lot of different ways where you're using AI techniques to get to the same problem, get to the solution faster. So everything is essentially focused on productivity. Now, everyone talked about the talent shortage. This is another one that we have. This is essentially to see how we can get that done. It all has Gen AI capabilities, Copilot capabilities. But the most important thing we do is every product within Siemens EDA. I think that will be the pretty much the standard going forward, will be an NLP interface going forward, where you don't need to learn a syntax. You don't need to, if you're running a spice simulation, you don't need to know how to write a measure statement. You can just say, do this, measure this. Sometimes you can even ask your Siri or something like that, voiceover, just a matter of time before it happens. But even the most complex analog kind of problems can be easily solved by engineers or just beginner engineers with less experience. So we're really focusing on that. So we're using generative AI to do a lot of things in terms of runtime analyzer to figure out where the bottlenecks are in your design or in your flow, in terms of assisting to write certain rule texts, write certain assertions using generative AI. So that's more important. And finally, an NLP assistant that can be not just your Docker assist, but integrated within the software products so that it has context to the design and what the designer is doing at that point in time in the flow, right? That's where we are looking at right now. So these are all almost there, or in some of the products are almost coming up in the next few months. And the last is, in terms of extending development cycles. So, Calibre has been signed off for a long time in terms of DRC and LBS. So we are actually coming up with, it's one thing to point out there are errors, but another thing to point out how to solve the errors in a much more efficient way. So there's a lot of insights built in right now using AI to actually make that happen so that you get to the sign-off stage as fast as possible. DESN is another product. So we launched SSN, it's a streaming scan network 3 years back, and it's been a huge success. Essentially, it uses unsupervised learning. It helps you optimize your scan insertion and scan testing in terms of I/O efficiency. It reduces in terms of your load time, time here in your load tester significantly, right? That's the real value that the customer sees in terms of cost reduction when we are actually doing design. So that's another product that we have. And another one is we have is in terms of yield management and silicon lifecycle management. We are actually using predictive AI and unsupervised learning to actually point out your worst yield contributors in your flow, in your design, and actually get to solve that problem at a much more earlier stage. So that's what we call test and diagnosis. So that's actually using AI as well. So ultimately, it's helping you solve your problem faster, correctly, and get to the takeout soon. And finally, we have another one called Solido Analytics. This is another one. So if you have anyone seen a .lib Liberty file, it's like terabytes long right nowadays. But how do you find inconsistencies and issues in the .lib? So we use AI on ML and AI and outlier analysis to actually easily find out what the issues are in a huge file, essentially solving a big data problem. So I think in summary, what I want to say is, we are doing AI for a long time. We are getting into generative AI. We're going to see more and more products coming up. But the most important thing I want to let everyone know is it's actually production grade, in the sense it should be mathematically correct as much as possible for the given use case. And that's what we strive for. And we offer that. And we offer AI workflow across the entire spectrum, all the way from design closure. It helps you in terms of fewer respins. How do you do resource planning, improving your quality of your design and logistics in terms of, reporting and everything else. So this is just a eye chart, but, these are all the different case studies we have where customers are using and getting the benefits of AI. But this is an interesting thing. I saw another presentation with a different format, but what it tells you is how we are using AI to do it, right? For example, Veloci and emulation side, we use reinforcement learning to figure out how to reduce compile time and to recompile. Because the compile is a huge amount of time that it takes in terms of emulation cycle. So we do that. We have with Tesson I talked about, we're using AI to reduce your test time improvement all the way from 5x. And we have analytics using, in terms of Solido Analytics to debug all your timing files, right, with 50% reduction. And with Caliber products, we have Recon User, right? We use AI to actually help you debug your designs much more faster, all the way up to 15x faster. So there are multiple examples over here, but the key thing is, AI is here. We've been doing AI. AI is there, and AI is definitely going to be helping you, reduce your productivity gap even faster. And I know it's just a matter of time before we also get into the latest stack that we're talking about, but it's coming. So this is just so I think the takeaway from this slide is all the products within Siemens EDA have some form of AI, and it's only investments only increasing to actually bring in more productivity gains for the users. So that's all I have. Thank you.
Thank you for the presentation. I'm glad you mentioned the research is happening in the world. I have a very general, naive, and a long question. You've mentioned the research, but I found that almost all the research are did by a group of engineers by using some old-fashioned, outdated AI algorithms. But if we look at the other areas, the breakthrough are made by data scientists, like biology, we got AlphaFold 2, and in MLP, we got ChatGPT. In video, we got Donald Trump dancing in a swimming pool video. But we've mentioned we using large language model, but large language model is designed for a chat robot. I think we probably need a specific model, specially designed for our area. And my question is, what if data scientists come to our area, or how we can attract them to this area? Will an EDA company recruit best data scientists without any EE background?
Actually, it's surprising. So almost 50+% or 50% of new engineers we are hiring are data scientists and AI, and who have expertise in AI, not the domain. It used to be different in terms of hiring before, right? You need to be good in physics, you need to be good in computer science and everything else, and then you start hiring people. But we are hiring a lot more data scientists right now. Your question about large language models, I think the large language model is a foundation model, right? The large is a problem, right? We call it domain-specific models. That's where things will go, specifically in terms of EDA, mainly because of data. I think someone was asking questions about what happens to the data, because data, it's similar to this, right? People say Llama is free, right? But Facebook Graph is not free. You can't access Facebook. Google can't access Facebook internal network graph, because that's their IP. Same thing in the same, if you have to say, have the same analogy on the semiconductor space, your IP is your IP, right? You can't let it go out, right? You have to put fence on something that brings you value. You can't just keep opening up everything and say, I'm going to innovate every day. That's not going to happen. You've got to have certain things. So I think the future is going to be on domain-specific models. There's a lot more research going on in SLMs, which we call small language models, which are very purpose-driven for a given flow or a given purpose. For example, for verification, you could have a model, and you have and the kind of I would say the development will happen in terms of developing those models, in terms of inference training, in terms of RAG frameworks right now. Things are going in the right direction right now. So to answer your first question, yes, we are hiring a lot. In general, everyone is hiring in terms of data scientist background. The second thing is, yeah, we are looking to bring in innovation within the product as well.
This is probably for all three of the big companies that have been speaking. So there's always been a sort of an uneasy interoperability between all the vendors. So although it takes pain to switch from Questa to VCS or to Excellium, it's a sales point. It works for the people to negotiate their own licensing deals, and it works for the EDA companies to add businesses. We've talked a lot about compound interest on the machine learning, learns on your data, and it gets better and better, and the more checks you're in. There'll become a point where the hit of transferring and losing all the data you've trained over the last 3 chips becomes a barrier to transfer. Are people thinking about how to overcome that now, or are we just relying on the fact that things will be so much faster in 3 chips time that you don't have to worry about?
From the EDA vendor side, I think my perspective is I think open is good, right? Definitely is good, but there's a reason why every product comes with their own strong side, right? If I have a strong product, I want to have a moat around it. That's the way the business works. I'm sure with other vendors the same way around. But you're right. I think when people are starting to build models, the model should be interoperable for their own sake. Else you will be locked into a vendor. And within Siemens EDA, even within vendor graphics, we've always been open. We're not having any in terms of closed ecosystem, open ecosystem. But you are correct. If you're starting to go work with the vendor and start building models which works only with that vendor, I would love to be that vendor. Right? That's the way it works. It gets too sticky.
Okay, thank you. Okay, yeah, so I'm just aware of the time, and we're probably getting quite hungry, so I'm going to keep this short. So I think I'm advertised till 2:30, but I'm actually going to finish at 2. Oh, no, it was just quick enough. Okay, so I'm going to talk about another topic you've probably heard enough of already, which is AI. But this is the TechWorks AI, and more specifically to TechWorks. Okay, so TechWorks do have a special interest group on AI. Okay, and they've been doing some work already. These are the slides from Gareth Edwards, who runs this special interest group. So it's not a network in the way DESN is a network, or the way that NMI or IoTSF is.
Not yet.
Not yet, not yet. Watch this space. But at the moment, it's a special interest group, and it's sort of cross-cutting as well. So it's it cuts across all those networks. So they've been doing some projects. Gav have been running some projects. And the first one we've done is a bit of materials, which, for those who know, there was a security one which was on the IoTSF. And Gareth has been leading projects similarly to look at basically a trustworthy bill of materials for AI. Okay, and that, I think that's coming to a close now, that project, isn't it?
Yeah, the project finishes late March.
Okay, late March, so it's coming to a close, but I think they're trying to get an extension on that as well. But I guess what we're trying to say is, if you're interested in AI, and then do get in contact with us, because we have this special interest group. It sounds as if it's going to turn into a network at some point. And it looks also look at the novel computer architectures as well, such as neuromorphics and robotics. Okay, so these are the topics it's covering. Again, it's led by membership. So whatever the membership wants is the types of things we start to look at. Okay. The reason Gareth can't be here at the moment, because he's an AI event in Bletchley, and we have another AI event in Bletchley coming on, which I'll tell you about. So within this special interest group, we're also looking at autonomous platforms and sensor fusion and regulatory horizon scanning. So hopefully these are obvious to people. Self-navigating on mobile platforms, also sensor fusion, where you're taking a lot of information from multiple sensors, like we do a lot on cars, the self-driving cars, and we're looking at the regulations that we do. There's a lot of regulations coming in, and so horizon scanning to just try and look at what the impact of that might be, if you're considering a product based on AI. Okay. So there's a tie bomb with a little bit more detail, and who we worked with as well. Okay. And Bletchley Park. This is the 25th of February. There is an event there today, but you're obviously here, but you might want to go to this one. On Bletchley Park, which is engineering trustworthy AI. Again, quite an important topic if you're actually trying to build products based on AI. And how can you trust them? How do you know that based on biased data, for example? These are the speakers you can expect at that event, and I'll leave that up so you can scan it and you can then register via that QR code. And I think that is the last slide, so we'll leave that up. And lunch is downstairs, Julian?
Yes.
Yeah, I'll just hand back to you to
Charles.
Charles.
Looks like it falls to me to be the, I don't need it, to be the what's standing between you and food. I'm starving. The sales pitch, yeah, this is the TechWorks sales pitch. Thanks, Mike. It's a shame Gareth couldn't make it, but as Mike said, he was away doing some other AI stuff. I just want to pick up on that and say that what we do, as I said at the beginning, fundamentally what we do is bring engineers together to collaborate in a meaningful way, cross-industry, cross-sector, cross-company, to help solve problems together. And typically what you find is you get a bunch of people in a room, there's plenty that they can discuss and collaborate on, even whilst they keep their proprietary information to themselves. And I think we've seen that today. We've got the three major EDA companies, the EDA industry in the room, and you guys have shared a lot of really interesting perspectives and information. And you know, I'm sure you didn't tell us anything you didn't want to tell us, right? But we've learned a lot, so it's been fantastic. And also, I'd like to say, Rod, great presentation on the chiplet stuff from ARM as well, which was really interesting. Going back to the AI thing, we are at that point now. We worked on this Trustworthy AI Bill of Materials project, which was funded by UK government, Innovate Project, bunch of companies involved, and that was our segue into AI. I guess I don't think this is a correct term, but kind of deep tech AI, right? You know, we're not we are about deep technology, engineering collaboration. So we're not interested in how do I write an app for a phone to book my holiday by speaking to it. But when you think about how do we develop significantly large LLMs, complex AI systems, some of which we've heard about today, and we ask ourselves the question: how do I trust this? How do I know it's unbiased, it's ethical, it's trustworthy, it's robust, it's unhackable? That's what the TIBON project has been about, developing methodologies and even tools to address that. And we will now continue that work post-project with a collaborative engineering kind of working group. And alongside that, we've identified by talking amongst industry other topics like how do I address new compute paradigms? How do I think about the application of AI to sensor fusion? And what does that mean in that specific area? So watch out for more information on that. If you want to learn more about any of the stuff, come to Bletchley Park. It's free to attend, 25th of February, details there. And then it just falls to me to check my notes and to say thank you to all of our speakers today. Thank you to our sponsors, Cadence and Synopsys, for helping us put this on. And thank you to all of you in the room. I think pretty much all of you are still here, so it's been a mammoth morning. And thank you to all the people online that have been watching wherever you are around the world. The speaker biographies are already on the DESN website, and the presentations and the recording of the session today will also be available soon. You will also receive, I think, in 7 minutes' time, an email survey. So please do fill that in, because especially with this being a new series of events, we want to make sure that it's valuable to you, and we want to at least listen to your feedback to make sure we get it right. As I say, we are planning more of these. The design network is kicking off now, and we expect actually the growth to be quite rapid. There's a lot of obviously appetite and interest and experience in the UK around this. And so we're going to do more of these on specific topics. So watch out for those. Julian is your go-to for all of that. If you have any suggestions, we're listening. We are also planning, as mentioned, a range of special interest groups. We have ideas for more than a dozen. We're not going to be able to stand up a dozen special interest groups in the next month. So we have to prioritize them. But if you've got any ideas, questions, thoughts, please come and talk to Gillian and myself. This will be around collaboration, innovation, maybe even project activities. If you want to know more, or if you want to join this network, DESN, just to be clear, we call it design. You know, we're doing a funky thing with the missing eye. You've spotted that, right? Yeah, I know. So please talk to Gillian or myself. That's it. Thank you very much. Enjoy lunch.